Hello, this is Jack Jackson. In this video, we're going to talk about areas of circles and regular polygons. So we're going to derive formulas for both of these types of shapes. So we're going to start with looking at areas of regular polygons. And notice that it's similar to what we did with Riemann sums, where we divide things up into rectangles. But here, instead of rectangles, we're going to look at triangles to divide it up. And so let's take a look at this picture here. This is a regular polygon, and this is a regular triangle or equilateral triangle. Regular polygons, remember, are polygons, so they have sides that are straight line segments. And they also have all of their sides are congruent, so the same length. We'll call that length S. And then they also all have these interior angles the same size. So this angle here at each corner, at each vertex, is the same. Now it turns out if you take the angle bisectors and if you take the perpendicular bisectors of each side, they all meet at a point called the center of the regular polygon. And so this distance that we have from any point from the center to any midpoint of a side, the length of that line segment is called the apothem when we use the A for that length. And the distance from the center to any vertex is called the radius. And so each of those radial segments are the same length. Okay, so each one of those is the same length there. Now the idea is, notice that we have then a triangular section here, and we know what this central angle is. So this angle here, if we go all the way around the circle, that's 2 pi radians or 360 degrees, and there's going to be one of these little yellow triangles for each of the sides. They're n sides, in this case n is 3, and so that is 360 degrees divided by n, or in this case 120 degrees, or in general 2 pi divided by n. And we're going to let theta be half of that. So theta is the angle formed by this apothem length segment and this radius length segment. So theta is going to be the measure of that angle right there. It should be half of that central angle. Okay, so that means that angle theta then is pi over n, or 180 degrees over n. Now, we have these for different sizes of triangles, different sizes of polygons, different ends. So there's a triangle, there's a regular quadrilateral, also known as a square, 5 sides, a regular pentagon, like the defense building in Washington, D.C. It's actually in Arlington. And then we can go to 6 sides, a regular hexagon, and 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 sides, and so forth. So we can, all of these are regular polygons, and at each one we have a little triangular slice, and you're going to have n of these triangular slices. So if we want to find the area, it's just n times the area of this yellow triangle. Well, we know the formula for a triangle's area, the area of the interior of a triangle, it's the base, which is length s, times its height, or altitude, which is the apothem a, times a half. So it's 1/2 as, but we have n of those triangles, so it's 1/2 as times n. Okay, so the area is 1/2 ans. But now n times s is the same as the perimeter of that. So another way to say it is 1/2 the apothem times the perimeter. And that's going to be our basic formula for the area of a regular polygon, 1/2 the apothem times the perimeter. And that's going to be probably our best formula, but there are other ways of doing this formula. Notice that this formula requires us to know both the apothem and the perimeter. Okay, now of course we need to know what n is to even know what the basic shape is, but we can get things in terms of n and any one of these variables, either if we know r, or if we know a, or if we know s, we can figure out the rest. And the basic idea is this. If we're looking at this larger triangle here, if you look at this triangle that's half as big, from the center to the vertex to the midpoint of one side, that is a right triangle, and theta is this angle right here, this central angle that goes right here in the middle. Okay, that angle. And remember we said it's of pi over n radians, or in degrees 180 degrees over n. Okay, so we have a right triangle, and we know that this side right here is A, the adjacent leg. We know the hypotenuse as length R, and we know the opposite side is actually half of S, so this is S over 2. And that gives us a right triangle. So we basically have this right triangle here where the angle's theta here, hypotenuse R, opposite side is S over 2, the adjacent side is apothem A, and we have, this gives us many relationships here among these four letters, A, R, S, and theta. In particular, one of them is the Pythagorean theorem, that S over 2 squared plus A squared equals R squared. But we also have the definitions of the basic trigonometric functions. The cosine of an angle is the adjacent leg, length of the adjacent leg over the length of the hypotenuse. That's going to be cosine theta equals A over R. Solving for A, we get A equals R times cosine of theta. Similarly, the sine of the angle theta is the length of the opposite leg over the hypotenuse. So that would be S over 2 over R. Solving for S, we multiply both sides by R and by 2 to get S by itself, so S equals 2R sine theta. The tangent of theta is opposite over adjacent, so that'd be S over 2 over A. Solving for S there, we get S equals 2A times tangent of theta, or solving for A, we get A as S over 2 tangent of theta. Now with these things and the fact that theta equals pi over 2 in radians, we can take those and put them in this formula, A equals 1/2 ANS. So let's see how that works out. So here we have A equals 1/2 ANS, and we can replace the S by 2A tan theta. Right here, this one, the third line. S equals 2A tan theta. Now put the A's together, you get A squared, you got an N. The 1/2 and the 2 cancel, and you still got this tangent of theta, which is tangent of pi over n. So we have n, A squared, tangent of pi over n, and that gives A as a function of n and A only. So certainly we need to know n so we know what basic shape we're talking about. And as long as we know that and we know the length of the apothem, we can find the area. Similarly, we can take 1/2 ANS and get rid of the A and put it in terms of S. Now A in terms of S was this bottom expression up here. A equals S over 2 tangent of theta. Put that in place of the A here in the formula, and we get A is 1/2 S over 2 tangent theta times N times S. So this half, these twos are both in the denominator, so they multiply together to get 4. Tangent of theta is in the denominator. And in the numerator, we have an n and an s times s. So that's ns squared over 4 tangent of pi over n. And finally, we can write it a different way as a function of both n and r by, let's see, a in terms of r is r cosine theta. So we can replace a by r cosine theta. And then look here, s is 2r sine theta. We still have our n, still have our 1/2. Now the 1/2 and the 2 are going to cancel, so that's going to go away. And that leaves us an n, an r squared, if you put those two r's together, a sine theta, and a cosine theta. Of course, theta is pi over n. So we have different formulas, several different formulas for the area of a regular polygon. It's 1/2 a n s. If you know n and s and a, you can figure that you can use that formula. You can use this formula, area equals n a squared times tangent of pi over n, if you only know n and a. You can use the formula a equals ns squared over 4 tangent of pi over n, if you only know s and n. And you can use the formula a equals nr squared times sine of pi over n times cosine of pi over n, if you only know n and r. But our most basic formula we want to think about is the one we started with at the beginning, that says the area is 1/2 the apothem times the perimeter. Now, so far, you might say, well, what's this doing in a calculus set of videos? Because, hey, there's no calculus so far. This is all pre-calculus. Well, let's take another look here at our picture here. And so let me go back to here and show you that there are a couple of circles we might look at. First of all, if we take a circle centered at the center of the polygon whose radius is the apothem, then that will be an inscribed circle. That circle will, the interior of the circle is completely contained in the interior of the polygon, and each side is actually tangent to the circle at the midpoint of that side. So it actually touches the polygon in n places. Now, if we take a circle centered at the center of the polygon and of radius r, it's going to touch each of the vertices, and that is a circumscribed circle. So let's back this up and look at what this looks like for n equals 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Okay, notice each time I'm fixing r, I'm not moving these points in such a way that r changes. And notice what happens. So r turns out to be a fixed number the way we're thinking of it here. But look what happens. As we increase n, what happens? Okay, several things are happening here. First of all, let's pay attention to what happens to the circles. As we increase the value of n, notice, well, regardless of where we are, the inside circle, the inner circle, the inscribed circle, has a smaller area than the polygon. And the polygon has a smaller area than the circumscribed circle. But what happens as we let n get bigger and bigger and bigger? These things get closer and closer and closer to the same area. Okay? At some point, it's very hard to tell the polygon apart from the circle. Okay, now look what happens to the apothem. Look at the length of the apothem. Now the radius is staying fixed. Every time I increase n, what happens to the apothem? Well, it's getting bigger and bigger. And the apothem is actually approaching what? It's actually approaching the same value as the radius. So A is approaching r as n approaches infinity. Hey, what are we talking about here? We're talking about a limit, right? So we have a limit process going on here. Now what about the perimeter of the polygon? What is it approaching? Well, isn't it approaching the circumference of that circle? So we're approaching, as n gets bigger and bigger, the circumference, the perimeter of the polygon is approaching the circumference of the circumscribed circle. Now, remember that all circles are similar, so when you do the ratio of the circumference divided by the diameter, circumference divided by diameter, it turns out you get the same number every time. Well, this number is a number that we call pi. In fact, that's the definition of pi. It's the ratio of a circle where you take the circumference and divide by the diameter. Doesn't matter how big or how small that circle is, that ratio will be the same. So pi, by definition, is the circumference divided by diameter. Of course, the diameter is just twice the radius, so pi is the circumference over the radius. Multiplying both sides by 2r, we see the circumference is 2 pi times the radius. Okay, so that really defines what pi really is. Now, we see that the area, if A is the area of the circle on the outside, we see that's the limit of the area of the polygon as n goes to infinity. The area of that polygon is 1/2 apothem times the perimeter. But as we take the limit as n goes to infinity, 1/2 of course stays 1/2, but A is approaching R and P is approaching C. The apothem is approaching the radius and the perimeter is approaching circumference. Circumference is 2 pi r, the 2 and the 1/2 cancel, and the r, we can write that with an exponent, and we see that the area is pi r squared. Now hopefully you saw this exact thing that we've been doing here back in elementary school or maybe middle school or high school somewhere along the way, and use this to derive the area formula for the circle. Probably you already know that the area is pi r squared. You may have forgotten that this is one way to get it. Now, we actually are using calculus here because we're taking a limit. So here's some calculus that you probably already did way back in elementary school. And although the limit language was introduced later, this method was used way back by Archimedes in the 3rd century BCE. So the roots of calculus go way back, at least as far back as Archimedes, who was using this. It was basically called a method of exhaustion. He didn't use the word limits at that point. But nevertheless, they're using what we would now call calculus. And by the way, Archimedes is considered one of the greatest mathematicians of all times. So that's very much in the same spirit as integrals, even though we didn't actually have an integral here, but it's still in the same spirit of it in the sense that we talked about slicing an area up into smaller pieces where we knew how to find the area from a simpler formula. Usually we've been slicing up with rectangles because that's probably the easiest thing to find the area of, and that led to Riemann sums. Here we're slicing up in triangles and finding those areas approximating the area of the circle with a bunch of triangles added up essentially, and then we take the limit as n goes to infinity to get the area of the circle.